Yeah. Yes. Who is this? Okay, so, okay. Yeah, I was just looking at that for a name.
Oh, me?
Okay, yeah, yeah. Hmm?
You can say change the point, different point, that's why they get that. When I change the point, I get such kind of different, this kind of picture, then after I just keep the one shot. Last one.
Okay, I have some serious suggestion for graphs. I have been giving you plots for some time. You all teach, I suppose, correct? Most of you teach. How many do not teach in a lab or something? You teach, so everyone teaches, correct? And you probably insist people on units. If there is an answer of 5, you have to bring in units, correct? Similarly, for a graph, you have to have units here. Okay, you have to have units there.
Or an axis title.
Axis title, graph title, everything has to be there. Otherwise, it is not even 11th grade submission. Like in 11th grade, it's acceptable. This is graduate level. Okay, it's not at all acceptable. And you have been consistently doing this. I try to mark it all the time, and no one seems to get it. So I want to suggest how computers deal with, like, let's spend 5 minutes on that, maybe. So let us say you want to plot y is equal to a, let's say sine omega t on a computer. How do you do this? Suppose I ask you to do this, ask you to plot it.
Right, Python.
Any program, I don't care. So now usually what I get is this, right? So usually what I get is something like this. And let us say some of you guys have done good. So you say this is time, right? So time, you even say this is in seconds. And then you would say y, let's say in meters. This is good, right? So when you do this much, that's already good. But then I see here, you will say this is 1, that's 2, that's 3, that's 4, and so on. So this is, if you say this is seconds, that's 1 second, 2 seconds, 3 seconds, and so on. And here you might probably say 1, 2, so on. Now, I don't understand this. Here there is an omega and an a. What happened to that? Where is omega? Where is a? So the way to work is that usually computers do not understand dimensional quantities. Computers, you cannot set t on a computer. What computer understands is dimensionless quantities. So usually what probably you guys do is, I don't know how you do this, but probably I'm guessing is that you set omega equal to 1 probably. Otherwise you cannot proceed. You have to set something for omega. Computer doesn't understand what omega is. So you have to set something. So another suggestion is that always set omega t, even if you set omega equal to 1, be aware that omega is equal to 1. So you set a dimensionless quantity tau, And so what you would do is y over a is equal to sine of tau or omega t, let's say this is y prime is equal to sine of tau. Now the computer understands, if you were to plot sine of tau, computer understands, and this is what you usually do in Python or whichever program you do. But you have to decode this, you cannot stop here. You have to decode this, if you say this is time, then you have to set. You have to set, so when this is equal to 1, now this is tau, right? Tau is equal to 1. So that means omega t is equal to 1. So t is equal to 1 over omega. So this is not 1, that's 1 over omega, 2 over omega, 3 over omega, and so on. This is a. This is 2 times a, and so on. So you have to undo it. It's very straightforward, but you have to do that clearly. So you, all of you, I think, I have not seen a single graph correct in the last couple of years. Consistently do this, and I think all of you set 1. But then if you set 1, t is equal to 1 seconds, then at least you have to tell me what omega is. If you set omega is equal to 1, then at least it is not wrong. But if you don't tell me omega, then I'm lost, right? I don't know what it means. Is that clear? How always redefine your variables, and it is in that variable that you're plotting. So here you say this is the scale of time. Like omega gives a scale for time, a gives a scale for a. A more complicated expression, you can redo this, you can divide out things by a certain quantity that is known, and you can rewrite your expression like that, and then plot it in dimensionless variables. Okay, so anyway, so that's a quick.
Weak but big relation.
Third,
Weak but big relation.
weak but
Weak but big relation.
big relation.
Relation.
Oh, listen, yes, that's correct, yeah. Or at least it's maybe
Is that.
it's the same feeling as when you have, when you don't see units on, and it's not the biggest issue. I know you guys understand it, but someone has to tell you, I suppose, and then you probably correct it. Okay. And you will see this in, you're very soon do this in papers, right? So somewhere you have to write it. And first time if you hand wave it, you tend to hand wave it all through, and you after a while you say, oh, I don't want to ask anyone because you're shy to ask. So fix this. Okay. That is the homework 4. And now the midterm is not too far. 1 week from Thursday. It's midterm. Those of you have not taken midterms, I think who's a Pradeep. I think homework is the best way to study. I think maybe you guys should be able to tell better what is the best way to study homework, and look for smaller questions in the homework. I more recently, in the last 2-3 semesters, or maybe last two years or so, I asked things that on an average was wrong while I was grading. So that's something that I picked up recently. So look for what you did wrong in your homework. And like these plots, I mean, but unless I correct it, I know that everyone will get it wrong. But those things, like I kind of ask in the exam. So look for what you got wrong. Yeah, so that's a and there will be 5 questions, I suppose. That's fine. 5 all short questions. It can be finished in 75 minutes. Surely 1 question on functional differentiation, 1 question on functional differentiation from the scratch, like from the ab initio group. I think those two I can clearly see. One question from your first homework, maybe something on drag or cycloid, right? Drag or something like that. Something that I have to come up with a question that can be done relatively easily in 10 or 15 minutes, in a sense. Yeah. So, yeah. So ask me again if I can be of assistance of how to study just the flip of 2 and 30. Okay, so we have introduced functional differentiation, especially think of the first example where we know Snell's law. This is how old is
Up to fourth homework or
everything that we cover until Tuesday before that. That's typically what I say, but then homework that is due, yeah, homework 4 is a good batch. But technically speaking, everything before the day of the exam, but homework 4 is a good measure, I think. Yeah, very clear, yes. Okay, so what we have done is functional differentiation. We talked about Snell's law, and yeah, I was just going to ask, how old is Snell's law? Any idea? Historically, is it?
I'm not sure, but it's 1921, 22 around the but you said.
That's quantum mechanics, time of quantum mechanics. Snell's law waited until then.
This will be Newton's time.
Yeah, even before Newton. Yeah, like even I don't know exact date, but it's before. It will be approximately 1600.
1600.
Yeah, yeah. So like 1900 becomes 2. That's quantum mechanics, right?
Okay.
We know light in terms of Maxwell equation.
I remember that day, 1921 or 22. I think that day, the quantum mechanics.
Correct. Quantum
Einstein or
mechanics.
someone, they produced new law at that day, 1921, and then they produced in 22. That's why we like only the day.
21, 22. Yeah, I don't know. Maybe, yeah. I think of Stern-Gerlach experiments around that.
Yeah, it's 10 relevant.
Yeah, but not sure. Yeah. Okay.
I remember the picture.
Yeah, but this is Snell's law.
Yeah.
I don't know how you connect with that. Okay, but anyway. So the idea is Snell's law was already always known. This is what we study in refraction. That's how light travels. That's the idea.
So,
Does it?
okay, sin x and sin x is.
Yes, n1 sin theta 1 is equal to n2 sin theta 2 at an interface. That's what we talk about. But then we said that that's all good, but Fermat's theorem is another way of looking at it. Fermat's principle, I don't know Fermat's theorem. I think Fermat has so many things associated with it. It's hard. Is it principle? That's not So here it was just saying something about the physical property of the medium. Here you say this is n1 sin theta 1 is equal to n2 sin theta 2. That's how you describe how light passes through an interface. Here you say that it is a time taken by light. Time taken by light between 2 points is minimized, right? So that's this apparently, or what we showed is that if we do differential functional differentiation, this implies that. So there's already a law existing. Law means it is able to explain a significant amount of data available using one equation, and a new interpretation is given for that. And that's Fermat's principle. Now, what we want to do here is we have Newton's law. And is there anything fundamental principle that can give you Newton's law in general, and this will be what will be called suggestive. Or functional derivative is the methodology. We used functional derivative to show that Fermat's theorem implies Snell's law. Functional derivative is just a mathematical tool that we use. Functional derivative is nothing fundamental in that sense. Fundamental, at least physics wise. In mathematics, maybe it has a lot of features in there, and we did not do functional derivative from a very, I would say, deep perspective. Like we just used this as a tool. For example, I never said when is functional derivative not possible. Like when you take a function and you take a derivative, you know that you need the function to be continuous to be able to take a derivative. I didn't talk about any of that. I just gave you a prescription in a sense, which seems to work. So we were not very careful in that sense when we were defining functional derivative. So in that sense, we are using it as a tool at a user level. Think of a computer, we're just a user, we are not developing the tool. Right, so, but at some point, we should start working on that also, but at least in this course, we are not doing it that way. And so we will use functional derivative go from here to there, and this will be called the stationary action principle. So first we should ask, what is Newton's law, right? What are we trying to explain? So what is Newton's, let's say, second law of motion?
Force equals mass.
Force equal to mass times acceleration. Let me write it as mass times acceleration is equal to sum of forces, so sum of the vector sum of forces, right?
Yep.
What is first law?
If an object is in motion, it will stay in motion.
Yeah, so mostly it is sort of defining what motion is. I think first is sort of telling us that it is not velocity that is important, it is the acceleration that is important. So that sets the stage for the second law. Because velocity, we are saying that velocity can be removed. Like I can always go to an inertial frame where velocity is not relevant. That's how one can look at it. And what's third law? The importance of that in terms of this. What if I remove that, and is there any problem? In the vector sum of forces. So consistency, I think that's what, so basically, if I have this for one mass, if I have this for another mass, then it should be consistent. What if I do M1 plus M2? So then all these forces should cancel each other, so that consistency is needed. So for consistency, we need. So we will, so when I say Newton's law, all three is understood, but this is what we have in mind. We have a lot of forces that we have come across. That is gravity, there is normal force, there is friction, there are drag forces, many forces, but many of them do not have expressions associated with it. Some of them are fundamental, especially gravity is fundamental, and we will talk mainly about conservative forces. Now, what is a conservative force? Let's say conservative force.
Fundamental forces.
Okay, something more precise.
Forces with expressions. Or
Yeah.
forces in which the derivative of the potential is a force.
Very good, very good. So, if you can write a force, if the force can be written as a derivative of a potential energy, negative derivative of a potential energy, not every force has an energy associated with it or potential energy associated with it. One is gravity, other is electrostatics or electromagnetism. That's pretty much it. You don't come across many forces that have a potential energy associated with it. Spring might be an example, like you have half k squared, but that's mostly a model. But yeah, so spring force, gravitational force, and electromagnetism are the only forces that you can think of as having a potential energy. And force should be written in terms of potential energy as a negative gradient. This is the statement that energy always try to be a minimum. What nature is trying to do is energy is trying to be a minimum. If energy is trying to be a minimum, the force will be a negative gradient, like negative of the slope of that is what's the force. So force we are seeing is a manifestation or a show of the nature trying to minimize energy. If you plot energy as a function of, let's say, one dimension, let's say x, and let's say electrostatics, so this will be u if you want. And if you take the derivative of this, derivative is negative now. There's a negative sign, negative of the negative makes it a positive. So force will be towards the right, towards the positive. Right, so force is negative gradient of potential energy. Take a derivative, it's in 3 dimensions, but in principle, take 2 points, calculate the energy, or another way of looking at it is here. Pick 2 points, calculate the energy, whichever is minimum, that's where it will go. That's where the chart, anything you keep there will tend to go. That's its natural tendency. And that's that statement for a conservative force. You can always write it as a negative derivative of a potential energy. We usually, when you're at least at most of the elementary physics or introductory physics books, we first learn the force and then the energy. What is the work done by a force?
Integral of the force.
Integral of, so
Integral of the distance or the path. of the
F
force.
started with dr. Let me write this on the other side. dr. And what is that equal to?
Equal to the work.
Work done.
Work done.
How is that related to the potential energy?
It's energy, work is energy.
Work is energy. How is it related to U, let's say the potential energy? Work is a energy, correct? How is it related to the potential energy?
Of energy.
So you go from initial to point, final? Right? And does it depend on the path? Work
Yes.
done, yes, so you're
That'll be a closed path.
work done from going from initial point to final point, right? It depends on the path typically. Typically, it depends on the path, but sometimes, only sometimes, very rarely, it is independent of the path. Like gravitational force and that's called a conservative force. If it is independent of the path, then you can define, so if it is, so when I cross this out, I'm saying it does not depend on the path, then it is defined to be a change in potential. Only if it is independent of the path does it depend on these two. Otherwise, it depends on the path too, so it is not a well-defined quantity. Like in thermodynamics, you usually come across quantities which are not, which are basically path dependent. They are not reversible. If this is the case, then you can define potential energy. So this is the inverse of statement. Notice derivative of energy is force, integration of force is energy. So now you have an inverse relation there, and which can be seen very clearly. If I were to, in the work definition, so dr dotted with force, if I were to substitute gradient of u, that's minus our initial to our final. Now this has become a total derivative. This is acting on a function that's a total derivative. So that simply says that minus of u, our final, minus of u of our initial. So conservative force has this statement. The second statement is that it has a potential energy associated with it. It also means that the work done along a closed path will be equal to. So
Zero.
very good. So dr dotted with f If it depends only on initial to final point, it doesn't matter which path I go. So if I come back on that different path, then I'm making a loop basically, and that will be equal to 0.
Same energy going in as coming in.
Correct. That's one way of looking at it. If you have a line integral of a vector equal to 0, what can you say about the vector itself? Vector calculus.
So then,
In electromagnetism, can you think of a quantity whose line integral is equal to 0?
classes of,
Or think of a line integral in electromagnetism. I think 0 is a special case there. Maybe I can ask
divergence.
Hmm?
Divergence theorem.
divergence theorem deals with surface, right? Not on line. So Stokes' theorem deals with line integrals, right?
Yes.
So Stokes' theorem says that
There is curly 0.
exactly, right? dl dotted with curl, Stokes' theorem is that
Is equal to the
is equal to, help me, so this is equal to some area, so that's dA dotted with curl of it. So if this is equal to 0, that means this also must be 0. We are having a finite area here. So this individually at every point should be equal to 0. And remember that there are many surfaces that can enclose a given loop. Is that clear what I mean? So when I'm thinking of a closed, so this is a closed loop, let's say. This is an area that, think of this is a circular loop, a plane circle is a area of the circle is enclosed by that loop. Even a hemisphere is enclosed by that loop. Is that clear? Maybe. Is that right? And I can build any balloon, for example, with that opening as its boundary, and all those surfaces have the same boundary. So it is important to realize that when you say there is a surface enclosing that, if I go from the left to the right, that surface is not unique. There are many surfaces, and that played an important role in Maxwell discovering the displacement current. That is how Maxwell basically, as a thought experiment, he could discover that quiz. Maxwell's term in Maxwell's equation. Maxwell's term, what is Maxwell's contribution in Maxwell's equation? What is, no, this is a question for you guys here. Sorry. What is Maxwell's contribution in Maxwell's equations? What did Maxwell do?
He was first to come up with light. Light is made up of like.
Before that, I mean, that was a consequence of what he did first. I mean, so Ampere's law, what is Ampere's law?
Oh, it's a closed loop around the current flowing wire.
Is that correct?
I mean, you take a current flowing wire and then you kind of place this.
So
A
that's
surface, you have a surface with current flowing through that surface, and what is the
so
current in versus current out? That's the flux.
So this wire creates a magnetic field, correct? And you take any loop, and if you calculate this B dotted with dl about that loop, what do you get? Current in it, right? Is that always correct? Is Ampere's law ever wrong? law, right? Law cannot be wrong, correct?
As long as there's enough data to support it.
Yeah, but has it been found that Ampere is wrong yet? Yes, no? No, right? One would think that law, but that's what Maxwell did.
Yes,
Huh?
if it is wrong, we can't use it, right?
It is wrong.
Yeah.
But I'm saying Ampere was wrong. Ampere's law is correct only in magnetostatics.
Oh, yeah.
Okay, only in magnetostatics it is correct. So if I say it is wrong, give me an example.
What took that, magnet and.
So here is that. So this is what Maxwell did. So this was Maxwell's proof of Ampere being wrong. So is this a familiar circuit? I'm going to enlarge this. We can put a resistance also. So that's R, and that's a capacitor, RC circuit, correct? So this is, let's say I switch the light on, or I switch this on at some time t, and we know how does the current go in this, or charge, let's say, current. Current as a function of time is, it will be, help me, so first it will be large and then it will go down, I suppose, right? So I think it is this, and it exponentially goes down. Correct, charge is that correct? Yeah, I think charge builds up.
Yes, on the capacitor.
So negative derivative of that, no, derivative of that should be. So, but there is an exponential of minus, I think it flips it and there's a constant, I suppose. I think this is correct, it starts, because after a long time, there is no current going, right, after there is sufficient charge. So this is the thing. So current changes with time. Right? So now, this is what's Maxwell's argument was. If Ampere's law is correct, again, building it here in my head, give me a minute. So what is Ampere's law? We have, help me, yeah, B dotted with DL is closed loop is equal to mu naught times I, correct?
Yep.
So I can take any loop and I should get the current going through that loop. So this is the loop he picked. Okay. And now, how much current is going through this loop? Let us say at time, small time, 0 plus delta. That's I naught, right? It starts from a current I naught. Is that all agreeable? So B dot DL according to Ampere would be mu naught times I naught in this loop.
Yep.
But then Maxwell said that that's not correct. Why is that not correct? This loop also is a boundary, has a boundary here,
It goes inside.
and it doesn't intersect. Like only when you think of this surface, I was talking about the surface that is intersecting the plane. How much current is going in depends on that choice of the plane. In this plane, it is mu naught I, as you would say. But in the plane that is going through the capacitor, there is no current. Right, so mathematically, that seems to be a problem.
Zero, there's no.
So it should be 0 here. So you would say, let's say this is surface S1, that's surface S2. So this is for S1, and for S2 is equal to 0. That's a conceptual problem. So Maxwell said that this cannot be true. We have to fix this. So he changed Ampere's law to have. To fix this, he said this is just not mu naught times I. It should also have a contribution from what is inside of the capacitor, and that is electric field is changing then, right? So it is d by dt of electric field dotted with dA. And here it is the surface enclosing that loop. And it is plus. And that is a mu naught. No, there is an epsilon naught. Epsilon. Right, BS, yeah. Think so. No. Mu naught. Okay, so that's the correction. Familiar, right? So that's what I was trying to point out. This is all going too far.
Yeah, yep, I now remember it. I remember we talked about this.
And this is called the displacement field, right? Displacement field, that's what it's called. Okay. But I was
Later
reading
on,
Newton's law.
whenever that mu naught and E naught, that's related to speed of light.
That's correct. That's where the moment you put this in, now you can have a wave equation for electric and magnetic field that
Gets.
gives you the idea that there is something which travels at the speed of light, which is a constant, which is a universal constant. Okay, great. Okay. Anything else on this? Quiz is write something about this is called Ampere's law. Ampere's contribution of Maxwell in correcting Ampere's law. So Ampere's law is coming back to Manuka. Ampere's law is correct in magnetostatics. Only when things are changing, then the second term does not contribute. So that's the idea. Okay, all this, yes, it had a meaning. That was because we were saying Stokes law comes in. Stokes law is whenever you have this. So that also means that a conservative force satisfies that del cross F is equal to 0 at every point. At every point when wherever force acts, it is equal to 0. So there are three different ways of defining a conservative force. Either one of them implies the other two. Right? Then you can only have conditions. We want to work with conservative forces. Exclusively with conservative forces, yes.
Like we took the concept.
We
Is
did
it
not.
not path independent, right?
So yeah, because I removed this, right?
Okay.
So I said path independent. That means if it is path independent, dr dotted with F is equal to 0.
Oh, okay.
Correct. For any force, if I can climb up the stairs, this west stairs and climb down and the north stairs, I'll come back. That's right. So that's implies using Stokes theorem. That's it. Okay. So we want to talk about forces that has this relation. That's the important piece I want to pick out of it, which is very rare, as I said. For example, if you take a normal force and ask what is the potential energy associated with it, we don't know that yet. So we cannot work with for normal forces in terms of Lagrange. But then we will find various ways of handling that also. We will talk about constraints. Normal force mostly are constraining a system to stay in a path, and we will deal with that. But most of the time, we are interested in these forces. So let me say that Newton's law is nothing but mass times acceleration. Let's say there is one force acting on it, and its gradient of u. U is a function of r, and in general, let's say it is a function of r or time. So I want to talk in terms of a particular case of Newton's law when the force can be written as the negative gradient of energy. And let's say the energy could be time dependent also, very general. And mass times acceleration, often maybe. This can be written as d by dt of mass times velocity, right? Let's write it in that form. Okay. Not every time you satisfy this, sometimes it's written in terms of momentum. Momentum is not always. Is momentum always mass times velocity? If you say no, then I'll ask you when is it not?
And try to think of a way.
Linear momentum, is it not mass times velocity?
Rotational or
That's angular momentum.
angular momentum.
Linear,
It's
it's mass times velocity. Yeah. Why would I ask you to? But I'm saying that now, sometimes momentum is not mass times velocity. And that is the case whenever there's magnetism. If whenever there's a magnetic field, there is a vector potential associated with it. Vector potential adds with mass times velocity, and then you say it is a canonical momentum, and then redefine your momentum. So, one has to be careful when we say this is momentum. But broadly speaking, what we have in Newtonian physics, introductory level physics, is that first we define acceleration, then force. Then force is usually associated with energy, potential energy, and acceleration is usually associated with momentum, right? That's how we write it. So let's stick to this for the moment. We will talk in your homework, you deal with electromagnetic case, so you will see situations where it is not momentum, but I don't stress on that. I don't write that down, just not to confuse you. But you will see that there will be a new term in here. So that's the shape of canonical momentum field. So that's your Newton's laws. And now we are saying that we would like to write this in some other form. Correct. So learning from Fermat's theorem, we want to define a quantity. In this case, it will be the action. So let me define this better. So for conservative forces, we want to define an action, say, or like first, let's say Lagrangian. And that's going to be equal to, it will, like earlier, we had, remember in Fermat's theorem, there was position, then there was derivative of position, and we integrate on some quantity. Here, there will be a trajectory. So this is the trajectory of the particle, so x as a function of time. So that's trajectory of the particle. Then we have velocity. This is the derivative of x as a function of time. So that's velocity. And it can also depend on t itself. So those are the three quantities we will have. But as you will see, this is a vector, right? X, Y, Z. Can have it as a vector. So the Lagrangian will be thought of as, depending on position as a function of time. It depends on velocity as a function of time, but velocity should not be thought of as independent. Once I know the position, its derivative gives me velocity. So at least at the Lagrangian level, we will have these two as the same. It should be written as, let me specifically write this as derivative, then there is no confusion. But it is velocity. Often in your homework and all that, it's convenient to write that as velocity just because typographically it takes less space. But x is the independent piece, velocity is only the derivative of that, and that is time. I'm stressing on that because very soon we are going to talk about Hamiltonian. Hamiltonian will have two independent variables, both position and momentum will be variables. It is momentum there, not velocity. Okay, and we will talk about it. So we have Lagrangian, and we define an action which is a functional now. That depends on an integral along the time of evolution. You go from, let's say, when you were born to when you died. In the lifetime of you being the system, T1 to T2, if you evaluate the Lagrangian, so this is x. Sometimes I also write r, right? X as a function of time. This is
position, velocity, and time.
position, velocity, and time. And what does it depend on here? It depends on x, right? As a vector, I don't show time because time is integrated out, right? It only depends on t1 and t2. So let's say you were born at time t1, and let's also give a specific time for your death. Most of you don't know that. Let's assume that, let me say my case so that I don't kill anyone of you. Say my case, like 20 years down the line, I'm going to die. So let's fix that dates. T1 and T2 is fixed. Now I can take many paths, right? I can come to Carbondale, I can go to some other city. So there are many paths possible, right? But actually, out of many possibilities, today I'm in this room. I could have been somewhere else. Right? Out of all those possible paths, my life picks a path. Right? That's a trajectory of me. And that's what we are asking in not in as complicated a system like life. It is not easy to predict life. But when I throw a ball up, it is very easy to predict that. When I put a charge in an electric field, we can predict that. Electricity and magnetism, when we throw a ball up or when we throw a spaceship into air, we can predict that. And that trajectory is got by minimizing this. So trajectory of an object is decided by minimization principle. So change the action with respect to now all possible trajectories, right? So all possible trajectories. So this is a vector now. Let's say t prime because I have used t prime and I set this to 0. This usually implies an equation. We did this for I when I used a general function I. This implies, so let's do this, right? Maybe as an exercise. Yeah, that can be. So I have, so now that we know functional derivative, that's my x is equal to t1 to t2 dt. And L, did I define that? Yes. Let's use R. V is derivative of position. That's T. What is the functional derivative of the action with respect to the trajectory? This will be equal to anyone?
Lagrangian.
So pretend that I'm taking normal derivative, right? So I first do the derivative as if I'm doing R, right? Notice this is x, y, z. We have been working with one variable. So there is 1, 2, and 3, and then you add up. That's what this means. Dotted now instead of doing this. That's derivative of R as a function of this is t prime. This is t. That's t. Thank you. So it's t. That's t, and that's t prime. Thank you. That's taking the derivative with this point. Then I can take the derivative with velocity. So that's dl by dv t dotted with something. What is this equal to? What do you multiply this with?
And then,
And
I think so. In 90 days.
the correct,
Would there be a dx or because velocity is
very good.
dr?
The time, right? That's what I was looking for, d by dt, right? d by dt of that variation. And the time variation, you don't worry about. Correct? You don't vary time, you're varying position here and here. Is that clear? Okay, that's what we learned in the last few weeks. Okay, it should be, at least you should have a feel for this. Only difference I made is that this is now position like vectors, so there is a dot product in which, so there are three of them in there. This is a time derivative on this. I want to make this independent. I put this, I integrate by parts, get it on the left, so there is a negative sign, or you can say this is a delta function, get it on the left hand side. So this is delta function, this time of three variables. Oh, t minus t. Only one, t minus t. So, and this is a delta of t minus t prime. If that's equal to, you have minus any questions on that? Okay. Action principle states, so stationary action principle or minimization. States that this action for the particular trajectory we are interested in, the real trajectory, is equal to 0. That means this equation, correct? So this is equal to 0. So that means d by dt. I move t prime to t, right? So this is t. So this is nothing but the gradient. Okay, so this is another way of writing a gradient. So this is not at all common, writing d by dr, but I will usually use that. Okay, most of the textbooks won't see that. Okay. This is called Euler-Lagrange equations. We want to see this as our Euler-Lagrange equation. Okay, so let's, and remember, I just threw something called a Lagrangian, but now I want to find the Lagrangian that corresponds to Newton's laws. This was a very general statement. This could have been any functional integral
This,
for that matter.
so with the stationary action principle, that's just minimizing the action.
Minimizing the action. What does action mean? We will think about that later, if at all we can. So it will be having some interpretation in terms of energies, but what we are saying is that there exists some Lagrangian, some function, whose integral, when I minimize, should give me Newton's law. This is not Newton's law yet, but I'm wanting to do that to be the Newton's law. So let's. So Newton's law is d by dt. Mass times velocity is equal, at least for conservative forces, that's Newton's law. If it was gravity, gravitational potential energy gradient gives me the force. And now I have Euler-Lagrange equations. The Lagrangian should satisfy this equation. thank you, yes, thank you. It's important. Okay, thank you. So that's dl by dv. There's a t dependence in there, so that's equal to L by dr. Remember again, d by dr is nothing but gradient. So we want to define, we want to have a Lagrangian which gives me this equation. I read it out, so there is a differential equation. The suggestion seems to be that maybe dl by dv is equal to mv. At least one solution may not be the unique solution. We have to ask, is Lagrangian unique or not? That's part of your homework also. And on the right hand side, maybe this is a gradient, right? So it seems like L can be just, or let me just say, dl by dr is equal to minus d by dr of u. Okay, so that's some conditions we have on the Lagrangian. Some properties of.
You're just relating the two equations.
Correct. I'm reading it out, like derivative of something is equal to something. Maybe, right? You can say maybe. At least if you say this is true, that won't be violated. If what you can argue is that you can put a constant in there, right? If there was a constant in here, which is independent of time, derivative of that constant will be 0. Right. So if I say d by dt is of f is equal to d by dt of g, then probably f is equal to g plus a constant with respect to time. Like only with respect to time, it can have any other variable in it. So we can, so that's the kind of conclusions I'm making. If derivative of something is equal to mass times velocity, what does that imply? So what is L? What can you say about L? Derivative of something is velocity, what can L be?
Exactly.
If I say dy by dx is equal to a times x, a is a constant, what can you say about y? Derivative of what is x?
X squared.
X squared, right? And probably half.
Yeah.
Yeah.
X squared.
So maybe L is equal to half m v squared. That's kinetic energy, right? Seems like, right? Surely that gives you the answer on the right side. But is that all? Is there something else? Remember, derivative of some constant can also get rid of it. So I'm not sure about this constant plus some function, like I've not used f of, but it cannot be velocity. It's a constant in v, and we are working in r and t, right? So what is remaining is just r and t. If I remove velocity, it can only have r and t, right? So probably this is a true statement. So I'm trying to see what Lagrangian could be. Okay. So, and now come back to this. Right. Now, what can we say from here? Right. If this statement is true, we can say that L is equal to probably negative of u, which is already there, right? R of t. But this is the gradient, right? So both the gradients, so it has to be independent of, so it can depend on velocity, right? Plus some g, which can depend on velocity and time. Right? And again, the same idea that if there was a velocity term, that will get killed in here, right? So I can get that same feature out of that. Reasonable. So together, maybe L is equal to half mv square. Again, our goal was that we get Newton's law by from this actual principle minus u of RT. Now I don't have R and V, but maybe there are still other possibilities, right? Maybe. So we will see that Lagrangian is not unique, not always unique, but for our purposes, these two will be our, at least one Lagrangian we will work with. And your question will be, for every Lagrangian that you build, you should be able to build 5 other Lagrangians, which will give you the same equations of motion. In your homework, I think it's the last problem, you actually address that. Okay, you build a Lagrangian and you ask what are the possible changes. So you will see that the total derivative of any function. So for our purposes, we will delete this and we say this is the Lagrangian, which is having a meaning in a sense. This is kinetic energy. And that's potential energy. Is this really true? Let's go back and do this for a simple example. One of the simplest example is gravity, right? Constant uniform gravity, or you can also have, yeah, let's do this for gravity, right? So
then you just set the constant of integration to 0.
yes, I wouldn't say 0. I would say that this is not unique. This is a Lagrangian. It is not the Lagrangian. It is a Lagrangian. It is not unique at all. So that constant that I talked about, I couldn't fix that. So I said, this surely satisfies that equation. I will have a Lagrangian that satisfies, that gives me Newton's law. It will turn out that there are many Lagrangians that can give you the same Newton's law, and they all have this feature that there will be total derivatives in time. So that's in your homework, and we can address that another part.
Okay.
So let's example. Something falling in air. I drop a small ball in air. Its potential energy is plus, right? Plus mg z, right? A ball, and this is ground. That's z. Right? From a ball is moving in vacuum. Let's say the air resistance is neglected. Potential energy is mg, so Lagrangian would be, and in principle, all right, V is m. It can move in all directions. Let's say V dotted with V. I'm emphasizing that it's a vector. It's V square, but Vx square plus V square plus Vz square, and minus of potential energy. Potential energy is nothing but plus mg r dotted with z hat, right? Right. R vector dotted with z hat is z. Correct. So that's just a putting it in 3 dimensions. That's all. Nothing changes. Physics doesn't change. It's a fancy way of it. And what is Euler-Lagrange equations? We should have this coming out, correct? Let's see. So Euler-Lagrange equations are this. So I first take the derivative with velocity. That's equal to mass times v. And this is the definition of momentum. Okay, this is called the momentum. Okay, or the canonical momentum. And that is what changes later on. Like we'll do an example for magnetism. If the potential had a velocity dependence, right? If the potential at velocity dependence, there is one term, mass times velocity comes from the kinetic energy. There could be a term that comes from this side also, if potential energy had velocity dependence. And magnetism is an example where there is velocity dependence. Remember the Lorentz force, that is QV cross E. So what is the potential energy associated with magnetism? What's the potential energy associated with electrostatics? Maybe let's begin with that. Uniform electric field, let's say. What's the potential energy? It should be in volts. Uniform electric field, uniform gravity. There is a connection. It is the distance, electric field, so mg dotted with, so here we saw, right? Mg with the direction dotted with z, right? Or vector. There it will be, this whole thing is electric field dotted with the distance, right? Whatever is the direction, if I'm going in the direction of the field, I gain energy in one direction, I'll lose energy. It depends on whether it's positive charge or a negative charge. Usually you just say this is E times D, right? Like we don't write it as a vector in introductory physics, we just say electric field times distance, that is equal to voltage, right? I think that's what voltage is, and so I need a force also, so if it is potential energy, it is Q. I can put a Q and then it will become U. Okay. Quiz, right? What is it for magnetic field? Little, probably not. But you're doing second semester of E&M, you will see it. Yeah. Or we will do it in the next lecture, you will see, but just let this be a quiz. Okay. Okay, so given the Lagrangian, first thing you do is always take the derivative with the velocity, and that's defined as a momentum. It is defined as a canonical momentum. Next thing you do is d by the position dependence. That's equal to, that is only r dotted with here, so that's minus mg z hat. What? Is it not readable? Is it readable? Euler-Lagrange equation is d by dt of the momentum now, canonical momentum, is the gradient of the Lagrangian, that's d by dt of mv, right? That's acceleration, mass times acceleration. This is minus mgz, is that correct? Yeah, because it's pointing in the downward direction. Right? So our units are all saying it is an upward direction. Right? So that's a vector. Newton's laws, or Newton's second law coming from the Lagrangian, right? This came from action principle, stationary action principle. Motivation clear? One of the nice forces we come across is the Lorentz force in electromagnetism. And what is that? What is the Lorentz force? A charge in an electric and magnetic field, what is the force it experiences?
QE.
So it is Q times E
QE plus B.
plus Q V cross with B. This has this nice feature that it is velocity dependent also, one of the rare situations where we have a potential energy for a velocity dependent force also.
QB to current.
current, what is it?
Current across the magnetic field.
Yes, that's correct, very good. That is a continuous distribution, yes, very good. So I think your point is that this can be written as charge, right, times electric field. And you integrate over EQR. That's what it means, so this is equal to plus J, very good. Crossed with magnetic field times R times T, yeah, that's very useful. So this is for a single charge. This is for a distribution of charge, it's a continuous distribution of charge in an electric field experiences this force. What is on the left hand side? It is equal to the mass times acceleration, right? So it is mass times velocity. It is the V, it is not the momentum there, so it is the mechanical momentum, if you want, mass times velocity. And yeah, I think this is also valid, but we will stick with this. Let's make it simple. Probably this will go through whatever I'm going to do. Not in the next 2 minutes, in the next lecture, 15 minutes for this also, but I would like to be safe. I'm not sure whether it will go through. So the idea is that we start from the same thing here, like this. And we want to find the Lagrangian that gives you the Lorentz force. Okay, quiz, what is the Lagrangian for the Lorentz force? And that's all. Next time we will do the Lagrangian for the Lorentz force, and you will, in the homework, do the same thing for the relativistic case. Have you guys done relativity to some extent somewhere? User? Relativity, little bit here or there. Yeah. Yeah. You've seen Lorentz transformation.
Yeah.
Yeah. Okay.